All right, we're going to take some notes today on Newton's third law. We call this the law of action pairs. But first, let's kind of remember some really important things we learned from Newton's third law. So we learned that if there is a net force on an object, what does that imply? Well, that implies that the object is accelerating. So if we flip that around, if we see an object accelerate, we know that the object must have a net force acting on it. So here's what I'd like you to do while you're at home. You're going to do this little activity, okay? You're going to find a wall, and you're going to stand flat-footed in front of it, so facing the wall. Okay, so your toes are going to be as close to the wall as possible with straight knees, and you're going to push the wall as hard as you can. Go ahead and pause this and do that now. All right, what did you notice? Did your body accelerate when you pushed off the wall? It should have. It absolutely should have. So hopefully you're going to put yes here. Okay. Now, why did you accelerate? We know from Newton's first law that if you accelerated, there must have been a net external force on you. There had to be. Right? There has to be. There has to be some net external force. So then, and this is the tough question, what object exerted the force on you? Now, some people might be thinking, oh, your hands or your feet or your legs. None of that is external to you. So the only thing that could have done it is something that you are touching. Well, what are you in contact with? You're in contact with the floor, right? Your feet are hopefully in contact with the floor. But that's not what caused you to accelerate. It was the wall. Okay, so the wall applied a net external force on you. You pushed on the wall, and then the wall pushed back on you. Well, not and then, but at the same time, okay? So here's a tough question. Which force was greater in magnitude? The force from you on the wall, so you're applying a force to the wall, right? You're pushing on the wall. I'm betting the wall didn't go anywhere. I mean, I'm not with you right now, but I'm betting the wall didn't go anywhere, okay? Or the force from the wall on you, and we know that you accelerated. So think about that and answer this question now, okay? Go ahead and pause the video and answer this question now, and then we're going to come back to it. Okay, so if you were in class with us, we did a little video, and I put a link to that video on our Canvas page, so you can go ahead and watch the video now, and you're going to see if you can figure out who exerts a bigger force. So what we've got, just a little setup here, is we've got two people pushing on each other with force plates. So a force plate, and here's the picture of the force plate right here, okay? So there's two force plates. So there's one person has one force plate, the other person has the other force plate. And all a force plate is a big bathroom scale, and we put some handles on it so that we could hold it vertically, okay? And we had two people sitting down in nice, easy rolly chairs, and they were about the same mass, and they pushed on each other. So go ahead and watch that video now and come back. Okay, so you should have seen the two people pushing on each other that were about the same mass, and you should have seen their results of their force plate, and you should have seen that the left person and their plate had about the same acceleration as the person on the right. So I don't remember the numbers, but you can watch the video again if you're interested, okay? So they had about the same acceleration. So when you watch them each fly backwards, they each went backwards about the same, okay? There wasn't a big noticeable difference. No numbers that we can look at for acceleration. Sorry about that. But then when we look at the force, we can look at the numbers, and those were the same as well. So those two people applied the same force on each other and got the same acceleration, okay? Then if you watch the whole video, you should have seen different mass pushers. So there was somebody in the chair, that was me, in the chair on the left, okay? And then there was a much bigger person sitting on the desk, still a rolly desk, and it rolls. There's not a lot of friction in the wheels. So it still can move, but had a lot bigger mass. And I think that you saw, so if you didn't watch it yet, go ahead and pause it now, pause the video now and go back and watch that other video. But what you should have seen, and hopefully what we saw, is that the person on the left side, that was me, they had a very large acceleration, right? I went flying through the door. I almost ripped the cords out. The person on the right had a very small acceleration. That's Mr. Higdon. Mr. Higdon on the desk didn't move very much at all. But what did you notice about the force? You should have seen that both of us read the same exact force on our force plates. So that's the interesting part, okay? That's the really interesting part. Now, why did I have much more acceleration? Because I had much less mass. Why did Mr. Higdon have a very small acceleration? Because he has much more mass. So what we're going to see as we go forward is that Newton's third law requires there's two objects and that they're exerting the same force, but the same force acting on different objects will have a different result, okay? So let's summarize what we saw here with our little experiment. And Newton summarized his law pretty much this way. And you might have heard it differently in middle school, but I like to say it this way because I think it's very clear, okay? So when object A exerts a force on object B always exerts a force on object A that is equal in magnitude but opposite in direction. Magnitude just means size. So we can put magnitude is the same as size, okay? And another way to say this is that the force of A on B is equal to the force of B on A, but there's a negative sign there. That negative sign just indicates that they're in opposite direction, much like we saw with velocity or acceleration in our kinematics unit, okay? So we say that these two forces make up a third law force pair. And there's a couple of different things you want to remember with third law force pairs. And this can actually be pretty tricky. People mess this up all the time. Okay, so how many objects are needed to make up a third law force pair? You need exactly two. Not one, not three. You need exactly two. It has to be two. So whenever you're thinking about third law force pairs, think of what are the two objects that are interacting, okay? How many forces make up a third law force pair? Again, exactly two. No more, no less. There has to be force from A on B, and there has to be the force from B on A, okay? We know that the magnitude, or the size, will be the same size. They have to be. They're just in opposite directions, okay? So one might be pushing to the left, one might be pushing to the right, okay? Does one force occur before the other, or do both forces act at the same instant? They have to act at the same instant. It's not a little brother, big brother instant where he pushed at me and then I pushed him, right? It's the same instant, okay? So it's happening at the same time. So here's what I want you to do. We're going to take a look at some instances, okay? And we're going to come up with some Newton's third law force pairs. So the first one has been done for you. It's pretty simple. If the fist hits the wall, what's the third law force pair? Well, the wall has to hit the fist, okay? Let's take a look at this next one. If the head bumps the ball has to bump the head. So I want you to pause the video now and go ahead and fill in these other ones and then come back and take a look and see what we've got, okay? All right, so let's go through these. If the windshield hits the bug hits the windshield. Now, which one do you think has the bigger force, right? Because the bug goes flat, but the windshield is just fine. But we know that they have the same force, right? That's a very trick question because one is so much smaller than the other. They still exert the same force on each other. It's just the bug undergoes a much larger acceleration and goes splat, okay? So if the bat hits the ball for C, obviously the ball hits the bat. We don't normally think of it that way, but it's true. If the hand touches the nose touches hand. If the hand pulls on the flower pulls on the hand, which is weird. We don't normally think about that, but it's true. And if the athlete pushes the bar up, the bar pushes the athlete down. And if the compressed air pushes the balloon outward, okay, then the balloon pushes the air inward. That's why the air stays in there. Now let's think of another one, okay? And this is a tough one. Let's think about the earth pulls down on a ball. Right, I drop a ball, the earth pulls down on it. What's the third law reaction pair? Think about that for a second. So when I'm trying to think about reaction pairs, I always think of, okay, well, what are the two objects? The two objects are the earth pulls down, or the earth and the ball. Those are the only two objects. So if the earth pulls down on a ball, the ball has to pull up on the earth. Well, we've dropped lots of balls in this class, and we noticed something, that when we drop the ball accelerates down. Does the earth accelerate up? I would say definitively no. Well, why doesn't the earth accelerate up? Why do we only see the ball accelerating down and not the earth accelerating up? Well, we don't see the earth accelerating up because even though there's the same force acting on the ball from the earth as the force that's acting on the earth from the ball, we know that the earth has a lot more mass, right? So the earth is not going to accelerate nearly as much, or frankly, almost at all. We could get a number to it, but it wouldn't be measurable. Okay. So we can see the ball accelerate. We cannot see the Earth accelerate. Okay. All right, that's it for our notes today. Go ahead and check Canvas and see, or Schoology if you're in a different class, and see what else you have to do for today. Thanks. Bye-bye.